kind of important to record the review day. Yikes, of all days to miss. Let's see here. You've got assignment 5, and I posted just assignment 5 short solutions. And so that way you can check your work just like a little bit, right? I'm not giving the full answer, but I am giving you just for the confidence interval, I'm giving you the confidence interval so that you can check your work. It's still your job to interpret it, kind of know what's going on. And then the same thing for the hypothesis test. I'm giving you the T and then the conclusion. Right? So for all of these, I've just given you the short solution, and then you can kind of work from that. Okay, so hopefully that's good. Another note, I'll write it down, but I will be here all day Thursday, all day Friday, all day Saturday, probably all day Sunday. So that's just how it is when I'm here in town. So if you have any questions and you're here, then just send me a text to make sure I'm here, and then you can stop by. So anytime. So, but usually I'm just always here. Unless I'm in Ottawa, then I'm not here. So, I don't know if you guys have had a chance to look at these, but there's also the extra practice problems that kind of go with assignment 5, or they're really more like chapter 5 practice problems. So where you're just going to read all these questions. I think there's 10 or so. Yeah, 10 questions, and you just read them and figure out what type of question they are, because that's really kind of hard to do, right? To read a question and try to figure out, okay, well, what type of question is it? Once you've figured out what type of question it is, that determines which region of the formula sheet you're working in, right? And then you don't stray from that part, right? So once you've decided what type of question you have, then it's kind of, I don't want to say easy street, but it's a little bit easier, right, to kind of get going. And so I posted the solutions, just the types, right? And I've tried to explain why. Sometimes it's just kind of, well, you've got 2 independent samples because the samples are independent, and there's nothing else I can say about that, right? But so have a look at those. Also, there's chapter 5 practice problems with solutions, with full solutions typed up. So you can have a look at those, kind of work backwards. And I just posted, well, it was hidden. Now I just posted it. The practice test 2 solutions, because as you noticed, it's really long. There's no way we were going to write out all those solutions in this time frame. And also because I wasn't sure on which ones everyone had done. So what we're going to do is we're just going to kind of work through these, and I'm just going to highlight important things that I think you need to keep in mind, right? But also, were there any specific questions that came up when you were working on the practice test? I know I only told you had to do 2, but so let me just check to make sure. Yeah, that's everything on Moodle I wanted to show you. So here's the practice test. Up here, I'll make a note that I will be my work, your school, at school. Thursday, Friday, Saturday, and Sunday. So stop by anytime or text with questions. So the format of the test, I know it's a little bit weird. I've done it before and people tend to like it. So just having options for which questions you're going to answer. And I think even as you were going through the practice test, it looks like you kind of had an idea of which ones you like to do and which ones you maybe don't like to do so much, right? And so I want you guys to feel like you can really do well on this test, and that's why I'm giving you the options. But like I said, so question 1 is on the test, right? So, or question 1 type of question, because it's a little bit different, right? It's going back, it's kind of like a throwback. So we've got something follows a normal distribution with a mean this and a standard deviation this. Find some probabilities, or here I kind of threw you for a loop and gave you a probability and asked you to find the cutoff value, right? And then I say, okay, now we take a sample. What's the sampling distribution? And then find some probability associated with the sampling distribution of X bar. And so here, remember what we do? So, well, I can't tell if I should go through it. I'll just go through it, but just quickly. I will go through and just double check. I actually just finished this last night and then I was like, screw this, I'm going home. So I haven't gone through to make sure there's no typos, but it should be reasonably okay. I'll go through it later, but so this one, I'm giving you a proportion, right? The 45, so how slow do the slowest 45% of West Indian manatees travel? Really what we've got here is we've got this here, normal distribution, right? Centered on 3.8 and sigma is 1.34, bless you. And we want to know how slow do the slowest 45% travel. So in terms of a picture, it would look like that. And so what do? We go to the Z table and we try to find the table entry that's closest to 0.45, right? And so going back to our tables here, we know it's going to be on the negative side of the Z table, and these here are all our probabilities, right? And so we're looking for the value closest to 0.45, and we land between 0.4522 and 0.4483. The one that's closest, if you just do a quick calculation, is 0.4483. And then we map that back to a Z-score. So 0.4483 maps back to -1 or -0.13. So that's the value of Z that you're going to use. Yeah. Oh. Remind me after. Okay. Oops. Chapter 5. Where did it go? Oh, there. Thanks. Okay. So then what we do, we just use the same formula. So we've got Z is, and it's not obvious that you're only talking about single manatees here. But the thing is, I haven't told you what your sample size is. And that's why you can only use this formula, right? So how question 1 is going to go is there's going to be a probability or find a cutoff for one observation. Then you take a sample of some size in part B. I ask you what the sampling distribution is, and then you use that in part C to find your probability. And so for part B, now I tell you that you sample 50 West Indian manatees. What's the sampling distribution of their average speed, X bar? Even if you just stopped here, that would be full marks. Oops. I get a little lazy and I just leave it like this in this form, right, over the square root of 50. I don't simplify it. You can if you want.
If we simplify it round, is it still good?
Yeah, but try to keep, I don't know, I'd say 3-ish decimals. Yeah. If it's not clear on the test how many decimal places you should use, then just ask me during the test. If you're unsure, then just ask. Yeah. So now, what is the probability that the mean speed, right? So now we're talking about the mean, which means we have to use our Z is X bar, right? That's the mean, minus mu over sigma over root n, right? So now we're using this information down here. What's the probability that the mean speed is less than 3.4 miles per hour? So we've got 3.4 is the mean observation, and then we can calculate our Z score to 2 decimal places. Remember, Z has 2 decimal places and T has to have at least 3. And so to 2 decimal places, we get negative 2.11. If you go to your Z table, you're going to find that the area to the left, which is the area that you want in this case, is 0.0174. And so the probability that the mean speed is less than 3.4 miles per hour is 0.0174. Any questions about that one? No, you don't. They will be helpful though. And sometimes if you draw the graph of what you think is happening, then at least if you're consistent with your calculations, I can give you part marks, right? Because then you're showing me, okay, here's what I think is going on. And then if you just follow through that way, you can keep more marks, but you don't have to, but I would recommend it if that helps. Yeah. Any other questions about that one? So there's definitely one like this on there, right? Just kind of a throwback to the Z scores. We're ready to move on to question 2. So on the test, I'll write in pink again. On the test, pick 2 of the following 4 questions. Mm-hmm. And then 2 more. Yeah. And then for the ones that you're not answering, you can just tell me what type they are. Give the type for the other two questions. Okay. Notice that the types are the names of the blocks on your formula sheet, right? And so we've got one sample means sigma known, right? That's when we're using sigma. And then we've got one sample means sigma unknown. That's when we don't know the population standard deviation, but we're using the standard deviation from our sample, right? So that'll be kind of in the question. You have to figure out, okay, between these two, where did the standard deviation come from? Okay. And then we've got matched pairs or paired data, and then that's when we've made 2 observations on the same subject, right? And then we've got 2 independent samples, or just 2 sample means, where we're just comparing 2 groups, the means of 2 groups. How do they compare? Okay. So on here, I've given you the type, and I've, again, tried to explain why. Sometimes, you know, it's just kind of obvious, but specifically for the one sample mean sigma known and sigma unknown, those are, I find, just people have a really hard time keeping track of those, right? And so for this first one, or second question, you took a random sample of 48 Amazonian manatees and found their mean speed to be 4.4 miles per hour. Assume it is known that the standard deviation of speeds for all manatees is 1.34. Okay. So here, this is all manatees, that's the population, making this sigma. Okay. So you'll always get a standard deviation, it's just a matter of where is it coming from. So here I've got one sample mean sigma known, since we're assuming we know the standard deviation for the population, so all manatees. Did you guys notice as you went through these questions are in order of the formula sheet? Okay. I do that on purpose. I did it on purpose because I don't know about you guys, but my mind, when I'm in a test, I always like kind of try to visualize what I did before. And so now, at least if you've worked through these in this order, then you can kind of link them back. Might be easier. I don't know. That's what I'm going for. I'm trying. So at least they're not all mumble jumbled here, but you've got practice problems that you can go through and read them where they are in mumble jumble order. So at least here you've got these kind of laid out. On the test though, they will be scrambled. Okay? Not the first one. The first one will be just first. So the question says, is there evidence that Amazonian manatees are significantly faster than West Indian manatees? So from the previous question, West Indian manatees travel at a speed that's approximately normally distributed with a mean of 3.8 and a standard deviation of 1.34. Right? Same standard deviation because it's the population standard deviation for all manatees. Okay. So this 3.8, this is the value we want to compare our sample mean to. Right, we've got a sample mean of 4.4. So X bar is 4.4. And I guess we've got an N in here. N is 48. Because what's tricky about one sample means questions is that we have to figure out, okay, so we've got a sample, we've calculated the mean, and then there's going to be some value that we want to compare our sample mean to, right? And so we have to read the question and try to figure out what that value is. And so here, right, we want to compare our sample mean of 4.4. Is it faster than 3.8? Right, so is it higher than 3.8? So first thing we have to do is our null hypothesis. Our null hypothesis is that mu equals, on the formula sheet, we just have mu sub 0, right, mu naught. But mu naught is the value that we want to compare our sample mean to, right? So we have to use 3.8 there. And then ultimately what we think is going on is that maybe the mean for the Amazonian manatees is actually larger than 3.8. And so we communicate what we think might be happening usually in our alternative hypothesis. Okay. Any questions about that so far? So I'd say figuring out what type of question you have and setting up your null and alternative hypotheses, that's the biggest job, right? Because now you already know that you're going to calculate a Z because you said you have one sample mean sigma known. So then you know that you have to calculate a Z, right? So that's not crazy. And so once you know that, then you can just plug in your values and we find a Z of 3.10 because Z has to have 2 decimal places. Here I've shown you what the p-value looks like. This area here, you can't even see it. Or I'll do this. This is the one-sided p-value. You can't even see it, it's so small. But you can use the Z table. So using the Z table, we find the area to the left of Z equal to 3.10 is 0.9990. Might have thrown an extra 9 in there, I don't know. So the area to the right is 1 minus that, right? Because the Z table always gives you just the area to the left, and then it's your job to know if you need the area to the right, then you have to do 1 minus the area to the left. So now you've got your one-sided p-value is 0.001. Super small. So our conclusion, this is the one that you're gonna memorize, right? You have to compare this p-value because what we're saying is we have to cross some threshold in order to reject the null hypothesis, right? And so our p-value has to be less than the alpha level. And I don't think I gave you one, right? No. So the default, remember, is 0.05. And so since our p-value of 0.001 is less than our assumed alpha level of 0.05, right? So it's less than the alpha level, we have enough evidence to reject H naught. And if you're rejecting it, may as well say in favor of what? In favor of HA. Therefore, there is evidence that Amazonian manatees are significantly faster than West Indian manatees. Any questions about that hypothesis test? So then, construct a 95% confidence interval for the mean speed of Amazonian manatees. Does this interval confirm your findings in part A? So for our confidence interval, we've got this formula. And again, because you've already decided what type of question this is, you already know what your confidence interval looks like because you just move down a step on your formula sheet, right? They're all in the same piece of land here. And if you don't have a copy of the formula sheet, I've got extras up here. You'll want those for studying. So we have X bar. X bar for Amazonian manatees is 4.4. And oh yeah, very cute. And we need Z star for a 95% confidence interval. We know sigma is 1.34 and we know N, we took 48 Amazonian manatees. And so we just need to find Z star. And remember the trick we used, so you could go through and use the Z table. That means you'd have to draw out, okay, you want a 95% confidence interval, which means you've got 5% leftover split evenly in the tails, right? It gets really messy. And so what we do is we just use the T table. Right? even though we want a Z star, I don't know if you guys, it was a while ago that we did this, so may as well review it. 95%, we can roll down to Z star, which is the third line from the bottom. So we have a Z star of 1.960. You can plug in those values, and here I went straight from plugging in the values. So I want to see the blank formula, just so that you show me which one, you know which one to use. I want to see the blank formula, I want to see the numbers plugged in, and at least I want to see X bar plus minus, and then I want to see the margin of error. Right? So this is kind of the minimal amount of work that you can show. And then this one is optional. This line, where I've given all the decimal places. I've rounded to 2 decimal places. As long as you round properly, you're okay. Once you have your confidence interval, we have to interpret it, and we use the same interpretation as always. We are 95% confident that the interval from 4.02 to 4.78, and one side note, if you've written these in reverse order, I have to take a mark or half mark off, just because it only makes sense from lower to upper. Right? So just check in with yourself and make sure that you do from the lower to the upper. So it captures the mean speed, or the true mean speed, of Amazonian manatees. The second part of the question was, does this confirm your findings from part A? Right? In part A, we said that the Amazonian manatees travel at speeds significantly faster than 3.8. If we look at this, right, this whole interval, right, it's all above 3.8. Right? And so this is confirming that yes, the speeds are significantly faster than 3.8. In fact, we're 95% confident that the speeds are faster than 3.8. And so I've written, since this interval is consistently above 3.8, I use consistently just to emphasize that while this whole interval is above 3.8, it confirms our finding from part A that Amazonian manatees are significantly faster than West Indian manatees. Any questions about that one? All right. So, moving on to question 3. An insurance company is reviewing its current policy rates. Something they should probably be doing. When originally setting the rates, they believed that the average claim amount was $1,800. They are concerned that the true mean is actually higher than this because, of course, they could potentially lose a lot of money. They randomly select 40 claims and calculate a sample mean of $1,950 with a standard deviation of $500. So here, I've only got one sample, right? One sample of claims of 40 claims, and so already I'm pretty sure it's a one sample means problem. The question is, do I know sigma or do I not know sigma? And in this case, because of the way the sentence is structured, right? You collect a sample of 40 claims and you calculate the mean to be this and the standard deviation to be this. This standard deviation is from the sample. Standard deviation is from the sample. Oh, I revised assignment 4 because remember I accidentally gave you a t-test, a one sample mean sigma unknown on there. It was not on purpose. It was just sloppy. So the question, if it's a chapter 4 type of question, right, sigma known, the question should have read something like, assume the standard deviation for all house prices is 94,300. So I did change that. It didn't actually matter because we hadn't covered where the standard deviation came from, so I was kind of safe that way, but just in case you're flipping back and looking at your assignment 4, then it's good to know that it should have been different. Okay. So here, the standard deviation is from the sample, okay, which means we have one sample mean sigma unknown, and oh yeah, part A just asks, should the insurance company be concerned? Use a hypothesis test with an alpha level of 0.01. So now I'm giving you an alpha level. Usually it's just a default, but now we have to use 0.01. And it's kind of, so should the insurance company be concerned? What's that actually asking? It's asking, is the mean claim amount higher than 1,800, right? They're assuming it's 1,800, but now we've got this sample mean of 1950, which is higher. We just need to know if it's significantly higher than 1,800. And so here, your null hypothesis is essentially no need for concern. And here, the alternative hypothesis is really when they should be concerned, right? Because then we're concluding that the mean is greater than 1,800, should be concerned. I've got little notes here. This is a one-sided test. And that's because I'm only concerned with one extreme. It's only if I have a not equal to in the alternative hypothesis that I have a two-sided test. So now, one sample mean sigma unknown. Again, your null and alternative hypotheses are kind of laid out. You have to figure out what mu naught is, right? The value that you're comparing your sample mean to. But then when you're ready, you can do the test, right? When you have your hypotheses laid out, you can do the test. And so we can calculate t, x bar minus mu over s over root n. And we find a t, and remember t has to have at least 3 decimal places, of 1.897, which is large, right? But just thinking about that threshold of, okay, anything beyond 2 is typically, we're going to reject the null hypothesis, right? So 1950 is above 1,800, but it's not quite significantly over 1,800. But we'll just confirm with our p-value. So now we use this t to find our p-value. If you've calculated a t, you have to use the t-table. Okay. And so it only shows, for some reason it rounds to 2 decimal places, sometimes around 1 decimal place sometimes. But the idea is the same, right? So here, this area in the tail is your one-sided p-value. To use the t-table, we have to find our degrees of freedom, right? And for one sample mean, the degrees of freedom is just n minus 1. We had a sample size of 40 claims minus 1, which is 39. When we go to the table, though, we find that we have to choose between 30 and 40. Right? And so we have to use 30 because 40 would be saying we have a sample size larger than we actually do, right? So we always have to bump it down. So you're going to make a note, say, but I'm going to be using 30. So you're going to show me that you know how to find it, and then you're going to show me that you know to bump it down if you have to. We find, and then here, we've been doing these for a while now, right? So we start and we do our calculated T. This is our calculated T in absolute value brackets, and I put them in the center of the page or wherever I'm working, right? And then I put the less than signs, and then I show the values on the table that that wrap around it. So we said we have 30 degrees of freedom, and so we've got 1.897, and I'm trying to place here, and I find that I'm somewhere between 1.697 and 2.042. So I jot those down, or you jot those down, and then I want a one-sided p-value, which is the first row of p-values, and so my one-sided p is between 0.025 and 0.05. The only switcheroo that you have to make is reading the p-values from right to left, right? Because they're actually decreasing as you move further out. Okay. It's just a range for the p-value, but we still are able to reject or fail to reject the null hypothesis. So since our one-sided p-value, and so our conclusion, you always want to show off what your p-value is. How does it compare to the alpha level? What does that mean in terms of your null hypothesis? And then finally, what does it mean in terms of the question? So since our one-sided p-value is between 0.025 and 0.05, it's not less than our alpha level of 0.01. Remember I told you what alpha level to use? So it's not less than 0.01, which means we do not have enough evidence to reject H naught. Therefore, the mean claim amount is not significantly higher than 1,800, so the insurance company does not need to be concerned. Any questions about that one? Okay. Here, remember we can use confidence intervals to test the hypothesis. And so should the insurance company be concerned, use a 98% confidence interval to test the hypothesis. And so we know our formula for our confidence interval. It's on our formula sheet. And so we just have to find T star. We already know that we have 30 degrees of freedom, and we want a 98% confidence interval. And so we've got here 98 meeting up with 30 degrees of freedom. Here 2.457. So that's how you're defining your T star. Same way as the Z star, but you just stop at your degrees of freedom. Okay. So I've got using the T table with, because you've already shown the work for calculating the degrees of freedom in part A, right, you could just say with 30 degrees of freedom, that's fine. And a confidence level of 98%, we find T star is 2.457. So now you can plug those values in and find your confidence interval. Because it's money, you know you have to round to 2 decimal places. So here, 1755 to 2144. Just looking at this, 1800 is in here somewhere, right? 1755 to 2144, 1800 is in there. It's just on the cusp, but still. Okay. So we're 98% confident that the interval from 17 to 2100-ish captures the true mean claim amount. Since 1800 is within this interval, the insurance company does not need to be concerned as the mean claim amount is not significantly different from 1800.
So using DF equals 30.
So yeah, so you have 39 degrees of freedom, but because the table jumps from 30 to 40, then you have to make a note of which line on the table you're actually using. Yeah. Good. Any other questions with that one? So as you've noticed, right, all these questions, hypothesis test, confidence interval, right? Part A, hypothesis test, part B, confidence interval. And so on the test, right, you've got question 1, and then you're going to do 2 hypothesis tests and 2 confidence intervals, and tell me the types for 2 others. So, if there are no questions about the question 2, let's go, or question 3, let's go to question 4. Alternative sources of energy are of increasing interest throughout the energy industry, of course. Wind energy has great potential, but appropriate sites must be found for the turbines. To select the site for an electricity generating wind turbine, wind speeds are recorded at several potential sites for 6 hours for a year. Every 6 hours, sorry. 2 sites not far from each other look good. Right, so we've got these 2 potential sites that we want to compare. Each had a mean wind speed high enough to qualify, but we should choose the site with a higher average daily wind speed. Okay. And so because we want to capture, so we're not making 2 observations on the same subject, but we are making 2 observations on the same day, right? So every 6 hours, we're making 2 observations. 1 at site 2 and 1 at site 4, it turns out. Okay. And so because we want to capture, there's really windy days, there's not very windy days at all, right? So we want to capture those differences. We've got a paired data type of question. Okay. So we want to record these as, or use the paired information, right, to make decisions about how these 2 sites compare. Right. Another kind of giveaway is that, okay, so I've given you the information for site 2, the information for site 4, that's fine, but I've also given you the information for site 2 minus site 4, right, which I would only give you the mean and the standard deviation of the difference if it was a matched pairs problem. Okay. So here, I'm going to say, well, here, this is the difference, which makes it matched pairs. Yeah. In a table or in the blurb, I'll give you the mean of the differences and the standard deviation of the differences. Okay. But if it's in the text, then usually I only give you the mean of the differences and the standard deviation of the differences. And I think we didn't go through it, but it's the tomato plant one in chapter 5. That's one of those where it's baked into the question. But also if you read through those question types where you have to read and figure out which type is which, you'll see somewhere it's in the blurb. Okay. But I like to just give it like this. Okay. So if you've decided that you have paired data or matched pairs, then even though I give you this individual information, you know that you can just ignore it because what you're going to be analyzing is the differences. So, like I said last day, if I was doing this test on Monday, I would be doing the matched pairs and the two independent sample means, just because those null hypotheses are already, they're set in stone, right? And so for me, when I read the questions, you know, for one sample means where you have to figure out, okay, what value do I have to put in my null hypothesis? For me, that's, I don't know, I don't, especially when I started doing this, it's hard, right? You have to read the question, figure out what you should put in your null hypothesis. But here, once you've decided that you have paired data, this is always your null hypothesis, right? So your null hypothesis for paired data is always that mu diff equals 0 or mu d if you want. So the question asks, is there evidence that either of these sites has a higher average wind speed? Kind of a tricky question because we've got the word higher in there, making us think that we should have a greater than in our alternative hypothesis, right? But because we're not specifying which site has to have the higher amount of, well, energy or whatever, average wind speed, right? We just want to know if there's a difference between the two, right? If one is significantly higher, we will find that there is a difference. And so this one's a little sneaky, and I'm not going to do something like this to you on the test, right? It'll be obvious, but it's always good to see these. And so your alternative hypothesis is going to have to be, well, it has to be about mu diff, and it has to be how does it relate to 0, right? And so the only thing that changes is the sign in the alternative hypothesis. And here we've got a two-sided test, just because we've got the not equal to. To do the test, we use just little subscript D's in class. Here, I copied pasted, so I'd already typed in the diff. So, but if you want to use just subscript D, you have to use D or diff though, just to indicate that, hey, I know I need to analyze the differences. But so nothing's changing, right? It's x bar minus mu over s over root n. Right? It's just what is it coming from? And so here we've got, we can calculate our t, our mu diff is always 0 because we always assume the null hypothesis is true, right, in our testing. So we find a t of 2.669, which is large, right? So we suspect that we're going to be rejecting the null hypothesis, but we have to find the p-value just to be sure. Notice for the two-sided p-value, right, we found our t of 2.669 is out here, but for two-sided p-values, we have to pretend that it happened down here as well, and take this area and multiply it by 2. Right? But the t-table does that for us. Right? If you notice the one-sided p and the two-sided p is just 2 times the one-sided p. So, so it just does it for you, but it's good to see it in action. Okay. So we had 1,114 as our sample size, right? Every 6 hours for a year, and the counts were in the table. Right? Count is your n. So to find your degrees of freedom, you're going to have n diff or nd minus 1 which is 1,114 minus 1, which is 1,113. But when you go to your table, you'll find you have choices between 100 and 1,000, and then Z star, which is infinity, right? Which we don't have infinite, we have 1,113, so we're going to use 1,000. Same idea, right? We take our calculated t, we stick it in between the absolute value brackets. It's between two values on the t table. And same idea, our two-sided p-values between 0.005 and 0.01. So now we know where our two-sided p-value is. It's small, yeah.
I'm just noticing if you took the one side.
Did I really?
I don't know if I'm
I just might have. Let's see here. What was it? 2.697? 2.669. Let's see here. 2.669 is somewhere between here and here.
oh, I see. I thought you had 0.005.
Oh yeah, but still, so 0.005 up to 0.01. Is that what I have? I'll check.
0.005.
It's okay. Yeah, they get, well, especially because they're just like, so between here and here, right? This one is here, and then, but this one is just 2 times up. Good. It's totally possible because, like I said, I did not proofread it at all. So it's good. So now we know our two-sided p-value is really small. So since our two-sided p-value is between 0.005 and 0.01, it's less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught in favor of HA. Therefore, there is evidence that one of these sites has a higher average wind speed. Remember, because we did a two-sided test, all we can say is that, yep, there is a difference between the two, making one have a higher wind speed than the other. Right? If you look at the data, so look at the information that we gave you, or that I gave you here. If you just look at the means, it looks like site 2 has a higher mean speed, right? So even though we can't say for certain because we did a two-sided test, right? At least we can say, okay, well, yes, there is a difference between the wind speed, the average wind speeds, okay? But looking at the data, we suspect that site 2 has a slightly higher average wind speed than site 4. Okay. Any questions about that one? Oh. Okay. Construct a 99% confidence interval for the mean difference in wind speeds. Oh, there should be a line break there. Using the t-table, so we set up our formula if we want to. We can just check and see, okay, well, I have X bar of the differences, I have the standard deviation, I have the number of differences. All I need is T star, so I'm going to start there. And so using the t-table, again, with 1,000 degrees of freedom and a confidence level of 99%, we find T star is 2.581. Now we can make this interval. Right? And so we just plug in our values. And again, if you have to show me the formula, you have to show me your values plugged in, and I want to see what the margin of error is. You have to show these three, but then if you skip straight to the rounded one, that's fine. Making the confidence interval is only half the marks. right? You have to interpret your interval. And so we are 99% confident that the interval from 0.007 to 0.401 captures the true mean difference in wind speeds. Okay. Any questions about that one? Oh. All right. Question 5. A factory hiring people to work on an assembly line gives job applicants a test of manual agility. This test counts how many strangely shaped pegs the applicant can fit into matching holes in a 1-minute period. The table below summarizes the data by gender of the job applicant. Right. Now we've got 2 independent samples. There's no reason to say, well, I'm going to match this female applicant to this male applicant and compare their scores, right? We just want to compare as a group, how do the males compare to the females? Right? And so then we have just two samples. We want to compare their means. And we can call them, I like to emphasize it by saying independent samples, right? But we can just call them 2 sample means. 2 independent sample means. If you want to. On the formula sheet, it just says 2 sample means because that's what it is, right? The independent is just emphasizing that they're just 2 separate groups that we want to compare. Remember what's neat about the 2 independent samples is that we can handle 2 different sample sizes. So in this case, we have the same sample size, which is fine. But definitely one giveaway is if you have different sample sizes for 2 groups, then it has to be 2 independent samples. And so, yeah, I don't know. I don't know what to write there. It's just, I guess you have to have all this information, right? So you have to have the sample sizes for both of them, you have to have the means for both of them, and you have to have the standard deviations for both of them, right? And so notice that I don't give you any differences, I don't give you the mean of the differences, I don't give you the standard deviation of the differences, and so it's just 2 independent samples. Is there evidence of a difference in the average number of pegs that males and females can place? Okay. So here, we want to know if there's a difference between the 2 means. Okay. In our null and alternative hypothesis, we have to use question-specific subscripts, right? So here, must use question-specific subscripts, doesn't matter which order, in H0 and HA. Because if you just have what's on the formula sheet, right, is mu1, mu2, then how am I supposed to know which one is 1 and which one is 2, right, and how they should be comparing? In this case, it's not that important because we've got a 2-sided test, but definitely if you want to show that one's greater than the other, right, you have to show which one's which first. Right? So this is a 2-sided test, because we have the not equal to in the alternative hypothesis. Okay. And here, I'll just highlight that the difference here is also what's making it a two-sided test. Okay. So once you've got your null and alternative hypotheses laid out, then you can do the test. Remember, the calculation here is a little bit bigger, right? Keeping track of, you have to square the standard deviations before you divide them by n. Right? And so I would spend a lot more time just kind of showing your work here in case something goes wrong. Right? Show your work, and then, but in the end, you've got a t, and once you have a t, you can just use the t table to find your p-value, and then it's just the same thing, business as usual. So we get a t of 2.478, which it makes us suspect that we're going to reject the null hypothesis, right, because it's larger than 2. But we'll find the p-value just in case. So again, we've got this two-sided p-value, and so using the t-table for 2 independent samples, we could use that huge formula for the degrees of freedom. It's not something I want you to do. I want you to just use the minimum of n1 minus 1 or n2 minus 1. Right? It's just saying pick the smallest of these 2 inside the brackets, right? Which is just going to be, we have the same sample size, right? So it's going to be the minimum of 50 minus 1 or 50 minus 1. Minimum of 49 or 49 is 49. Right? Again, you're facing that dilemma, right? You've got a choice between 40 and 50 degrees of freedom, or is it 40 and 60 even? I don't know. I can't remember. No, 40 and 50. So you have to go down to 40. You find that the t that you calculate is between 2.423 and 2.704, and you can find your two-sided p-values between 0.01 and 0.02. I didn't give you an alpha level, so we assume it's 0.05. So since our two-sided p-value is between 0.01 and 0.02, it's less than our assumed alpha level of 0.05. Both of these are less than 0.05. This means we have enough evidence to reject H9 in favor of H8. Therefore, there is evidence of a difference in the average number of pegs that males and females can place. Finish it off with a confidence interval. Here, remember what's nice is if you've done all the work in part A for finding this huge square root, you can say that, well, I know that this is 0.59737 from A. So you don't have to show the work again, right? You can just reuse it because you have shown me that you know how to calculate it once, and so then you can recycle it. Even if you wanted to, you could say, well, this is, what was it, 1.48 from part A. So then the only new thing that you have to find in your confidence interval, you still have to show me the empty formula, right? What you're plugging in. And then show me the values like here. So you can jump straight from show this and show this. This one's optional. This one's optional. I guess show the next one too. And then this one's optional. In terms of how much work do you have to show? you have to show the formula. You have to plug in the values. You have to find or show the margin of error. And then you have to show the rounded answer. We're 99% confident that the interval from 0.16 to 2.8 captures the true difference in the mean number of pegs that could be placed by men and by women. Any questions? Oh. And that's it. So like I said, question 1 is on there, right? Or that type of question. And then pick 2 of the 4 that you want to do. Tell me the type for the other 2 for 1 mark each. And then you'll be good to go. And like I said, I'll be here, well, basically up until the test. So stop by anytime. I have assignment 4s if you haven't picked them up. And I've got some blank practice tests still. Like what the, same as, so here, like I said, so question 1 on here, one of those. No. Yeah. So here. There you go. I've got some blank assignment 4s.